Welcome to Snacks Weekly on Data Science. This podcast is all about making data science and machine learning knowledge accessible and less intimidating. Today, we are going to talk about experimentation. This topic is based on a tech blog with the title How Meta Tests Products with Strong Network Effects, written by the data science team from Meta Platform. You can find the blog link in this episode's description. Throughout this episode, we will dissect the topic from both business and data science angles. Now, let's dive in. On the business side, let's take a look at the problem to be solved. Network effect refers to the phenomenon where the value of a product or service increases as more people use it. Many products today have strong network effects, and we engage with those products on a regular basis. Think about social networks like Facebook and communication platforms like WhatsApp. They all have strong network effects, as with more friends joining the network, its value for each user also increases. Network effect enhances a product's value for each user, and companies with such products constantly optimize their features to improve customer experience, maintain their network advantage, and to try to maximize value for their users. When it's time to decide on launching a new product change, A/B testing is commonly used to evaluate product change's impacts. In a standard A/B test, users are divided into a control group and a test group, with a new feature or treatment applied only to the test group. The performance difference between these two groups is then interpreted as the incremental benefits brought by this new feature. However, in environments with a strong network effect, standard A/B testing faces unique challenges. Users in the test group may interact with users in the control group. This could lead to two main problems. One type of the problem is undertreatment. This occurs when the experiments rely on users being in the same treatment group and resulting in fewer interactions of the type we are trying to test. For example, if a new calling feature is only supported when both users are in the same treatment group, because users in the test group may receive phone call from users in the control group. This is like the test users receive a lower dosage of the feature than expected. This makes it harder to observe the treatment effect, and often lead teams to run larger experiments to counteract this issue. The other type of the problem is called spillover. This spillover problem happens when interaction between test and control users cause misinterpretation of results. For instance, if test users can use a feature while talking to control users, the behavior of control users might change as well. This interaction can shrink the observed difference between the groups and increases the variances in both. Essentially, control users also receive a dosage of the test experience. This complicates the interpretation of the results. Now you know about the network effects and the challenges they pose to standard A/B testing. Let's shift gear and explore potential solutions to these challenges. The data science team at Meta analyzed how network effects influence experimentation and concluded that a well-designed experiment should not only introduce an effect, but also contain it to make it measurable. To achieve this, it is crucial to isolate, test, and control users, enabling a better comparison between their interactions. This is why the team chose the cluster experimentation method. Applying this cluster experimentation method involves two main steps. First, users are assigned to clusters based on who they interact with the most. Second, users are randomized to treatment groups based on their clusters. This ensures that all users in the same cluster belong to the same treatment group. This approach is known as randomization by cluster, then exposure by user. In this experimentation setting, under-treatment cases are dramatically reduced because users who interact with the most are always in the same treatment group. This boosts the user of interactions within the same group. Spillover effects are also reduced because the control and test users are based in different clusters. This makes it less likely for them to interact with each other. Now we understand the general methodology. Let's look at the specific algorithm used to build out the clusters. The team leverages a modularity maximizing graph partitioning algorithm. To better illustrate how this algorithm works, imagine a network of friends where each person is a node, and each friendship is an edge connecting two nodes. You want to find the groups of friends who are more connected to each other than to the rest of the network. And this is what modularity maximizing algorithm trying to do. They try to find these tightly knit communities. The algorithm starts by treating each person as their own community, where everyone is in their own little bubble. Then, it considers moving each person to a different bubble to see if it makes the network more modular, meaning more connections within the same bubble and fewer connections between different bubbles. For example, if moving one person, Alice, from her own bubble to Bob's another person's bubble increases the number of friendship within that bubble and decreases connections between bubbles. You choose to make that move. This process is repeated for everyone in the network until no more beneficial moves can be made. The next is to treat each bubble as a single node, and then repeat this process. Along the way, merging the nodes in each bubble into a single node, and then looking for new bubbles within the simplified network. Continue repeating the local optimization and aggregation steps until no further improvement in modularity is possible. This process helps to identify the most cohesive communities in the network. Eventually, you may end up with a set of bubbles where the connections within bubbles are much stronger than the connections between them. These bubbles represent the communities or clusters in your network. With the power of this modularity maximizing graph partitioning algorithm, a set of clusters can be generated. This leads to the question of how to evaluate the quality of these clusters. The team uses several metrics to assess cluster quality, including basic ones like the number of clusters and the distribution of cluster sizes. Besides these common ones, two most important metrics are called purity and the intra-cluster correlation coefficient. Purity measures the percentage of interactions and their values contained within the clusters. The intra-cluster correlation coefficient measures how correlated matrix values are for users within the same cluster. Let's focus on the purity matrix first. If each user is in their own cluster, the purity matrix would be 0. This scenario represents classic user-randomized experimentation, which is considered the worst possible isolations comparing to cluster experimentation. So, any clustering that increases interaction isolation is an improvement over not running a cluster experiment. Then, let's look at the second matrix, the intra-cluster correlation coefficient. This metric impacts the effective sample size of an experimentation. One foundation assumption of A/B testing is that users are randomized to treatment independently of one another. However, by intentionally clustering users based on their interactions and then exposing them to the same treatment, we ensure that while clusters may be independent, the individuals within them are not acting independently. In this way, a non-zero intra-cluster correlation coefficient effectively shrinks the experimentation sample size comparing to a traditional A/B testing assumptions. With these two clusters, this creates a trade-off between experimentation power and the purity of the cluster across two spectrum. On the left of the spectrum extreme case, it is called each user is in their own cluster. This is basically user randomization, and purity is 0, but statistical power is at its highest. On the right extreme of the spectrum, this is called mega clusters with all interactions included. In this scenario, purity is 100%. But without a control group, the statistical power is effectively 0. The ideal balance lies in between this spectrum, where both the power and the purity are optimized for the experimentation. A common approach to achieve the optimal stage is to generate a set of cluster candidates through a hyperparameter sweep, evaluating each for between-group interactions and the minimum detectable effect size required by the experiment. This helps to find the optimal balance, or the Goldilocks zone, for the experimentation. Now we discussed both the business problem and the technical solution. Let's wrap it up. In this episode, we discussed what are network effects, how they introduce challenges in the standard A/B testing framework, and how the cluster experimentation method can be leveraged to address those challenges. We also delved into the technical details of how clusters can be generated, evaluated, and the associated trade-offs that needs to be considered. If you like the content of this episode, please subscribe to the channel. Give me a 5-star review and leave a comment. Your feedback is greatly appreciated, and I'll see you next week.